today is the last day. For those of you who might need to take off earlier than the end of the day, we do have some surveys. If you have time between sessions, at lunch, etc., please try to fill one out. It does help us improve for next year. Lets us know what you think. So there's a bunch of them up here. If you fill it out, please leave it with Jim. And we'd really appreciate that. I think we'll get started. So, last day, Leo is going to finish off telling us about SMT solvers and how to deal with quantifiers and applications.
Okay, yeah. Today I'm going to talk a little bit about quantifiers, and I plan to spend most of the time talking about applications of SMT solvers. Okay, when you have quantifiers, the problem is more complicated because first order logic is undecidable, right? And in principle, if you have a arbitrary formula, you may not be able to solve it, right? But one point that's important is that for some theories, I mean, suppose that you have just linear arithmetic, right? You can eliminate these quantifiers, right? There are quantifier elimination procedures for linear arithmetic, for data types, right? But usually it's not just that. You're going to have interpretive functions, and now this quantifier elimination, there is no quantifier elimination procedure in this case. If you have extension quantifiers, you can use columnization to eliminate them, but still, you end up with several universal quantifiers that you don't know what to do. I mean, you have to instantiate them or to handle them in some way. And the problem for detecting insatisfiability remains, right? And more importantly, most people think, I mean, the theorem prover, the main goal is to prove theorems, right? But in practice, what you really want to know is show something is not a theorem, right? There is a bug in your program, right? Or the formula is satisfiable. That's your end goal, right? For a tool like SpecSharp, like what Rusin was showing, nobody cares when it proves, right? So a user of SpecSharp doesn't care when something is proved. It really cares when the tool detects a bug and tells you, here is wrong, here you made a mistake, right? That's what's the value of the tool. I mean, this makes sense because a developer usually, he thinks his program is correct, right? And if you just say, yeah, you're right, I mean, he thinks your tool is useless, right? Well, your tool is really useful if it can detect bugs, errors in your program, right? But now we have a problem, right? I mean, first order logic, in principle, you can write a theorem prover for first order logic that when the formula is unsatisfiable, eventually it's going to be able to show it that it's unsatisfiable. But it may run forever when it's satisfiable, right? In this way, we have this problem, I mean, a theorem prover that wants to return quick answers saying, I found a bug in your code, it's probably you return false positives, right? He's going to give up after a while and going to say, oh, I cannot prove this formula. Here's some information, I mean, some partial model, I think, for your formula. But this may not be a true model, and you may give a wrong information to your user. And if the rate of false positives is really high, everybody's going to stop using your tool. Well, I'm going to cover, basically, I'm going to try to invest most of the time on the e-matching approach. That's heuristic instantiation. E-matching is used in most SMT solvers. But there are other approaches also that are useful. One that is very important is decidable fragments. First order logic is undecidable, but there are several fragments that are decidable, right? In this way, if you can encode your problem in one of these decidable fragments, this is great because now you can return, when you say set is really satisfiable, you can give 100% confidence to the user that the formula is really satisfiable. This way, it's important to support decidable fragments. Another approach is to combine SMT with superposition calculus. Superposition calculus is an engine. I mean, the most modern first order theorem provers with equality implement this engine, and they are an alternative is to combine SMT with superposition calculus. Okay, before we describe matching, let's describe a new normal form. We talk about CNF, right? But if you want to apply columnization, right, you have to, one thing, you can view columnization as putting it in your preprocessor that we described before. But before applying columnization, we have to put in negation normal form. What's the point of the negation normal form? is that negation only shows up in atoms, right? You don't have negation in a sub-formula. You don't have not of something or not of exists. Why this is important? Because some quantifiers, you may think that here, for instance, in this example, you have this universal quantifier. It's not really a universal quantifier. It's an extension in disguise. If you move the negations inside, right, to apply this algorithm, you're going to find out that actually this universal quantifier is actually an existential one, right? In this way, basically here, the NNF is just applying De Morgan, right? You have, for instance, let's get one rule. You have the not of phi 0 and phi 1 is equivalent to what? Not phi 0 or not phi 1. It's just applying De Morgan, right? That's the whole idea. Now only the atoms have the negation sign. And another thing is that every sub-formula, we know that or it's true or it's a don't care, right? And now it's completely clear that this sub-formula here is extensional quantifier instead of a universal in disguise. Okay, after we do that, you can apply scolemization, right? The idea is that you can replace an extensional quantifier, right? Suppose that you have a formula, this exists y, where this formula f contains several universal variables that I'm representing by x, and the extensional one that I'm calling y. Now what I'm going to do, I'm going to replace y by f of x, right? Why this works, right? This gets clear with an example. Suppose that you have this formula. For all x, p of x implies that there is a y such that q of xy. Now I can replace this extensional quantifier and have an equisatisfiable formula. Here what I'm saying is that there is a f that maps x to a y, right? Such that for all x, p of x implies q of x, f of x. It's like the function f here is saying which y, right, you should use for every x. That's the whole idea, right? Again, two formulas are not equivalent, right? They are just equisatisfiable. Right. Okay, after we do that, we have only universal quantifiers, right? What do we do now? Well, one approach is the heuristic quantifier instantiation, right? That's used by several SMT solvers. The idea is that you view each universal quantifier. You can view each universal quantifier as an infinite conjunction, right? And we know one important property of first-order logic is that if something is unsatisfiable, you just need a finite number of instances. You don't know which ones you need, but you know that you need only a finite number of them. In this way, you can reduce the problem of picking the right ones. What are the right instances, right? And the matching comes from the observations that something is relevant, right? One of these instances is relevant if I find several parts of this instance in my formula, right? That's the whole idea. And how can I find these fragments in my formula? I basically select some patterns, some non-ground terms in my formula f, right? I'm going to try to look for instances of these fragments. If I can find these instances, great, I instantiate the quantifier. And for doing that, we put an extra. We're not just using a simple matching algorithm, a standard matching. We use matching modulo equalities, right? It's more powerful. For instance, we have here an example. Suppose that you have this pattern, f of g of x, comma x, right? This doesn't match f of a, b, right? There's no substitution for x that's going to make these two terms equal, right? But suppose that we have this equality, a equals g of b, right? Now, I mean, assuming this equality, I can say that x is b, right? We have f of g of b, b. Since g of b equals a, you have f of a, b. In this way, they match now, right? That's the whole idea of matching. But let's be more precise. What's the problem? What's the match problem, right? The idea you have a set of ground equations, right? We have a ground term t, and you have a pattern p that may contain variables, right? And now we want to find a substitution beta, such that the set of ground inequalities is going to apply this equality. I have an example here. Suppose we have these two equalities, a equals f of b and a equals f of c. we have a ground term g of a, and we have a pattern g of f of x. Here is another important point of matching. The solution, there is no single solution. You can have several solutions, right? Actually, in matching, you can have exponential number of solutions. And basically, I'm saying here that substituting x with b or c, you can match these two guys modulo these equalities, right? This is easy to see because a of equals f of b and a equals f of c is going to imply that g of a equals g of f of b, right? Basically, I'm instantiating x using b, I'm using beta 1, and the same thing for beta 2, right? You know that g of a equals g of f of c if a equals f of c, right? Okay, basically here we have two properties. One really important property of matching is that you can have several solutions. Oh, another common mistake that people do is to assume, oh, I can use standard matching, I don't need matching, right? I can do just substitution, right? I substitute a with f of b, right? Now I use standard matching. But if you do that, you're going to get one solution only, right? Suppose I substitute a with f of b. You're going to get one solution, x equals b, right? But you miss the x equals c solution. Now you can say, oh, let me substitute a with f of c, right? Now you get only x equals c, you miss the x equals b solution, right? In this way, it's not apply substitution and using standard matching is not the same thing as using matching, right? Okay, matching is an NP-hard problem, right? You can encode graph coloring problem using matching. The number of matches can be exponential. And the most important thing is a technique for handling quantifiers based on matching is not reputationally complete. I mean, you may ask, what does it mean to be reputationally complete? I mean, we say that a procedure is inference system is reputationally complete if whenever a formula is unsatisfiable, if you keep running your inference systems or your algorithm for an arbitrary amount of time, eventually you're going to be able to show it is unsatisfiable. Matching doesn't have this property. In this way, in some sense, it's really bad, right? Because, I mean, you may terminate to saturate, and you create all instances you could. Now you found something that looks satisfiable, but it's not. I mean, this is not a reputationally complete system, right? In this way, you can really have false positives. In a first-order prover, you only get a false positive if you give up, right? That basically 3 scenarios, right? You run and you find the formula to be unsatisfiable. Great, this is right. You run forever, right? You don't terminate. You do not terminate. You keep running this stuff forever, or you saturate and you can say that it's satisfiable, right? But in practice, what people do, they can give up, right? They say, oh, I'm giving up after 1 hour, and say I don't know. But with matching, is even worse, right? You can terminate saying unset, fine is unset. You may give up, it's like the first order prover based on saturation. Or you may terminate, but still, when you terminate here, doesn't mean it's satisfiable. Okay, matching is NP-hard, you can have exponential number of instances, but the real challenge, these are not really problematic in practice, right? Usually, we don't experience this problem of producing exponential number of instances. What's really problematic is that you have to, this matching procedure is embedded in this ZPLL engine that's doing a backtracking search, right? We are making the guesses and we do back jumps, right? In this way, you have to do this matching rounds incrementally, right? You don't want to match everything after every decision, after every time you increase your partial model, right? And in some cases, you have a large pattern, a large database of patterns, right? And you want to handle this database efficiently. Okay, let's see a precise description of the matching algorithm, right? The idea here is that you have this matching function. You have the first argument is a pattern. The second one is the ground term we want to match. And S is the set of substitutions, right? The first rule, I'm basically matching a variable against a term, a ground term. There are two cases here. Basically, I'm going to, S is a set of substitutions. I'm going to try to extend them. For each substitution I have inside of S, I'm going to do the following thing. If inside of this substitution, pick one of them, right? And now if this substitution I selected, if it's already binding X, I check if the value of the binding of X is in the same equivalence class of T. If it is, fine, I keep it. It's the second line. In the first line, the substitution I selected, right, is not binding X. In this way, I just say X goes to T, right? I save this information. In this way, the first line is just telling us how to extend each substitution inside of S, right? The second one is easy. If you have a constant and a term, you just check if C and T are equal in the same equivalence class. If they're in the same equivalence class, you keep S. If they are not, you failed. You cannot match. In this way, you just erase all substitutions you have and you keep the empty set. You return the empty set. And now the tricky case. When you have application, f of some patterns P1 to Pn, and you want to match against T. What we are going to do here is that for every F application inside of the equivalence class of T, we are going to do the matching. We are going to try to match the arguments, right? You are trying to match the first argument, the pattern P1 with the arguments T1 and T2 with P2 and so on, right? We are sequentially composing these calls, right? That's why here's the case where it's very expensive. You can have several F applications inside of the equivalence class of T, and in principle you have to try all of them, right? And if you want to know the set of substitutions, you just execute, right? Sorry, it should be P here, P of T, with the starting with a set of substitutions containing only the empty substitution. Keep in mind that I'm using the empty set with different meanings here. I mean, you have here an empty set of substitutions. I mean, I don't have any substitution. Here is representing a set with only one substitution that is not binding anything, right? We should be clear this distinction. Let's see an example. I have here the F data structure. I mean, our find structure, right? Saying I'm saying what is the roots of the equivalence class of each one of these terms, and I want to match T and P, where T is F of CB and P is F of G of X, age of XY. You can start doing calling the match with a substitution set that contains only one substitution, the empty one. Now, if we see F of CB, inside of F of CB, this equivalence class contains two elements, right? F of CB and F of G of A, B, right? In this way, I have to consider both of them, right? In this way, I'm going to have two recursive calls to match, right? And I'm going to do the union of the solutions from here and here. Right? Now I'm going to try to match age of XA with B, right? Basically, I have to look for, in the equivalence class of B, right? Where are the ages? I mean, you have an age application there. Yes, we have. Age of AD goes to B and age of CA goes to B in this way. These guys are equal, and I'm going to consider them for a matching. Again, it's like I'm considering two calls, right? One matching the arguments AD and another one matching the arguments CA, right? Now we go to, we're going to match AD, but A and D are not in the same equivalence class. In this way, what happens? I'm going to replace this guy here with the empty set, right? This matching failed, right? And since, I mean, if you have the empty set, there's no way to extend. I mean, there's no substitution here to extend. In this way, you just keep returning the empty set, right? Now match A with A, we succeed, right? We just return the empty substitution. Now we have match X with C. X and C this substitution, empty substitution, is not binding X at all, right? In this way, you just extend substitution with X going to C, right? Now we have the empty set union this substitution set with only one substitution. We get the obvious result. And now we have to match G of X with C, right? Inside of C, we have three G's inside of the equivalence class of C, right? We have G of A, G of C, and G of D. They are all equals to C. We are going to consider all of them, right? And here, it's easy because if we look carefully, you're going to see that A and C in the same equivalence class. Both of them, the root is C, right? In this way, we are fine, right? We don't need to binding X to C. Since X is already bound to C, I'm not going to do anything. I don't need to, here I should bind the X with A, but A is equivalent to C, I'm fine also. I don't need to do any update. But since D is not in the equivalence class of C, I'm going to fail the third one. In this way, we get that. We do the union operation, that's our result. We can do the similar thing for the second pattern. And we are going to get, oops, I'm going to the wrong direction. I'm going to get the same set, and that's the result of the matching, right? You have just, in this example, just one substitution binding X to C, right? That's more or less how the matching works. And here's a very small example showing how to use the matching for instantiation. Suppose that you have this quantifier f of g of x equals x, right? This quantifier may seem very simple, but this is actually used in practice, right? Basically, this is a really compact way to say that the function g is injective. It's a good exercise to see that's really the case. Let's assume that we are using the pattern f of g of x here, right? And you have this set of atoms, right? You have this conjunction. A equals g of b, b equals c, f of a different from c. If we don't instantiate the quantifier, this conjunction here is satisfiable. But if you apply the matching algorithm, we are going to see that the pattern f of g of x can be, we find an instantiation setting x to b, right? If we do that, we create this instance, f of g of b equals b, and after that, we can detect, oops, we can detect the inconsistency, right? We have f of gb equals b, but b equals c. We get f of gb equals c, but f of g of b equals f of a, right? By congruence, since a equals g of b. This way, we get a contradiction because we know that f of a is different from c. Okay. This algorithm I described for doing matching is very inefficient, right? He's moving this set of substitutions around, right? There's an argument that's a set of substitutions. And it's interesting, one point I remember one intern tried to implement the matching. He exactly implemented the abstract description of matching. And it was very inefficient, right? He had like a vector of vectors, and he was moving around this vector of vectors, doing unions and adding elements. It was very inefficient, right? The right way to do this matching efficiently is using you can do it in several ways. One point is you can do using a backtracking search, right? You don't need to keep carrying a set of substitutions. You keep only one at a time, and you backtrack to find the others. But if you want even a better performance, you can get you can build an abstract machine. The idea is that given a pattern, you can compile this pattern in a set of instructions. It's like doing partial evaluation. You generate a set of instructions that's going to match, is like the matching for that specific pattern, right? And you generate this code sequence. And you have in your theorem prover abstract an interpreter for this code sequence, right? Basically, you're generating specialized code for matching each pattern. But you can do even better. You can combine in practice, we have several similar patterns, right? And you could try them to match them simultaneously. One thing that you can do is combine these code sequences in a code tree. Basically, you're going to try to factor out common pieces of code that would allow you to match several patterns at the same time. Another problem is how to find new matches incrementally, right? So I'm going to talk briefly about this inverted path index. And finally, another thing that's important in matching is that when you're creating these clauses, these instances, most of them are completely useless, right? And it's really important to be able to garbage collect them. An efficient SMT solver should be able to identify instances that are not useful and delete them. Okay, let's go back to the matching code trees. Right, I mean, I said that you can partially, given a pattern, you can write a specializer that generates a sequence of operations that's specialized for matching that pattern. Now, as I said, you can have several patterns that are similar. You can combine them in a code tree. The main idea is to factor redundant work, and now you can simultaneously match. You can do matching of several different patterns simultaneously. This idea, I mean, this some form. I mean, we have been saying in every lecture that decision procedures you need indexing. You need some form of indexing. This is another form of indexing. It's important to point it out. In saturation-based improvers, they use different forms of indexing, and they also use code trees like that, but for something completely different. For implementing forward subsumption or demodulation operations they have there, they use similar techniques for implementing these operations efficiently. You can learn more about indexing techniques in the handbook of. I will send the link. I will put the link in the slides in the end. I forgot the full name of the handbook, but there is a full chapter about indexing techniques. Incrementality, right? Any SMT solvers, modern SMT solver is going to choose some form of VPLL. This is a backtracking search. In this way, you have to find this. You have to apply the match incrementally, right? Why you have to do that? There are two cases. The first case is that you create new terms during the search, right? Like in standard matching, if you create a new term, you may match this new term with some pre-existing pattern, right? This is default, right? But in matching has a extra complication, right? Is because you get new equalities during the search, right? What may happen is that suppose in the beginning I had only f of g of x and f of ab, right? They don't match, right? But suppose in the middle of the search, right, by using unit propagation or using the decide rules that we have seen before, we assign a equals g of b. Now that when you merge the equivalence class of a and g of b, you can match now these two guys, right? In this way, when you have a matching, there's this extra complication. When you assign new equalities, you may create new opportunities for instantiating these patterns, right? In this way, we have new terms. This is the easy case. Standard matching has the same problem. And the second one is the extra complication of matching. The inverted path index, I'm just going to give the abstract idea here. The idea is that when the idea here is when you merge two equivalence classes to find which terms were affected by that, right? Basically, you put the idea here is that you have a set of patterns, right? You want to know which ones were affected. And the idea is that you can follow these paths, and you're going to find in the nodes of this inverted tree the patterns that are affected by this merge, right? That's the general idea. I'm not going to waste more time discussing that. Okay, limitations, right? In matching, I mean, the main problem of matching, if you don't have any ground term to begin with, it's not going to do anything, right? I mean, suppose that you have a trivial problem that's unsatisfiable. You have for all x, f of x less than or equal to 0. For all x, f of x greater than 0. You send that to a SMT solver that's only using matching, nothing else, no extra heuristic. It's going to say, terminate. I cannot do anything. There's nothing. There's no ground term to instantiate to match against f of x. This way, there's nothing to instantiate. It terminates. But this is. I think everybody can see this is unsatisfiable, right? Another problem with matching is matching loops, right? Suppose that you have a pattern like you have two quantifiers. Suppose that you are using here the pattern is f of x and here the pattern is g of x. Suppose that I have a f of a, right? I'm going to match x with x can be substituted by a. You're going to get g of f of a. Now you can instantiate this guy with f of a, and you're going to get fg of f of a, and now you can do with g of f of a. You can keep doing that forever, this cycle, right? There are two problems here. One is inefficiency, right? You're going to keep creating probably a bunch of useless stuff, and you can also have non-termination. Some SMT solvers, they have heuristics for detecting these matching loops automatically and block the instantiation. One simple idea that we can use is that we create a chain, like whenever you create a new term, you mark which quantifier was used to create this term, right? And you keep creating these chains. I mean, after the chain, for instance, in this example here, we create f of a using this guy. F of a was used to create g of f of a. G of f of a was used to create f of g of f of a, and so on. You're going to create these links. I mean, if you get something that's really deep, you stop using these guys for doing a matching. Okay, concluding matching is incomplete, right? It's not reputationally complete. This looks bad. Saturation engines like superposition calculus offer strong alternatives. I mean, at least for first-order logic, they are reputationally complete. I'm making some propaganda here. We have a paper about combining SMT with saturation engines. And just to finish the quantifier part, an alternative to using, if you want to get high confidence that your problem is really satisfiable, one alternative is to focus on decidable fragments. In our TM prover, basically, we implement two fragments. One is this Bernard-Schofinkle class. The idea of this fragment is that you can only have universal quantifiers. You can have predicates, variables, and constants. You cannot have any function symbol, right? This class can be decided in any XP time. I mean, it's really expensive in the worst case. It's no deterministic exponential time. Just to check, even if someone tells you the answer, it takes exponential time to check it's really right. But this fragment is nice because, for instance, you can encode QBF in this fragment. You can encode useful theories like partial orders. Suppose that you support these fragments, you don't need to implement a decision procedure for partial orders. You can just encode the partial order axioms, and this fragment can handle that, right? And you can also use this fragment for looking for finite models, right? You have an arbitrary first-order formula. You want to look for a finite model for this arbitrary formula. You can use this fragment for doing that. Another important fragment is the array property fragment. This fragment is very useful for stating properties about arrays, like the array is sorted. I mean, this chunk of the array is equal to this chunk of this some other array. You can actually, with this fragment, you can verify procedures, right? Quick sort, merge sort, and so on, using these fragments. And the idea that, I mean, in Z3 we plan to support more fragments in the future. But that's one thing that you have to keep in mind. I mean, decidable fragments may be a good alternative to this heuristic instantiation. Okay, now I'm going to talk about applications. I mean, I try to summarize most of the applications we have in Microsoft. We try to make some propaganda again. We have our TM prover Z3. It's basically the development. The development of Z3 is driven by internal customers, right? There are people like Ruston and others that keep asking new features or asking us to improve the performance, and this is really helpful. With Z3, you can access Z3 using textual inputs. You can write formulas using SMT-lib format. You can use the simplify input format. Right? So if you are using simplify, you can automatically replace this by Z3 without changing anything. And Z3 also supports APIs. I mean, you can use access from your program using C or C++, .NET. .NET means Visual Basic, C#, F#, or any other .NET language. You can also use from OCaml, right? It's free for non-commercial use. Z3 is very efficient. In the last competition, from the 15 divisions, it got 9 first places and 6 second places, and it's available on this website. And you can find much more documentation about Z3 there. Here's a comparison with Simplify on the spec sharp benchmarks, right? Some of the benchmarks Ruslan had. Basically, in this graph, each star is a little benchmark, right? And basically, he is saying, at this point, he's saying that for this guy, Z3 took 0.63 seconds and Simplify 13 seconds. Right? Points below the diagonal is where Z3 is faster, above is when Simplify is faster. And this logarithmic scale, like in this point here, Z3 took 0.09, Simplify took 500. This is just to give an idea that Z3 is very efficient. And here was one of the challenges, because Ruslan wanted everything to be solved in less than 2 seconds. All was his first challenge for Z3. And only one guy took more than 1 second. Here's a list of the applications we have. Basically, I'm going to talk about test case generation, right? How to generate test case automatically using a tune prover. We have the verifying compiler, spec sharp. Ruslan already covered this part. I'm not going to talk about spec sharp. But I'm going to talk a little bit about Havoc and VCC. There are 2 other verifying compilers from Microsoft. I'm also going to talk about model checking practical abstraction, how SMT is used inside of this kind of tool. Okay, test case generation. Testing is 95% of the deal, right? In Microsoft, for every developer, there is one tester. Not in research. In research, we have to test and develop ourselves. But in the development teams, for every developer, there is a tester. And the developers have to write unit tests, right? And there are several tools. I mean, there are tools for annotating codes. I mean, you can do static analysis. And one thing that I'm going to concentrate now is file fuzzing, right? And how to automate file fuzzing. Security, I mean, the most important bugs from the point of view of Microsoft are the security bugs, right? They're the bugs that are really expensive and cost several millions of dollars, right? And most of these exploits are initiated by using files or packets, right? What the hacker does, it changes slightly a file. He sometimes builds an invalid file that's going to trigger a segmentation fault or allow him to do to exploit an access violation, right? And they do several exploits, right? If you can get a right access violation, this can always, in principle, can always be exploited. A read access violation sometimes, right? So you can also have null pointed reference, division by 0. It's not clear you can exploit this kind of bugs, but at least you can do a denial of service attack exploiting this kind of problem. Okay, the main techniques that black hats use to attack is this black box fuzz testing, right? The idea is suppose that you get a valid MPEG video, right? You start changing this video, creating possibly an invalid one that's going to trigger a bug, right? And a naive one just keep doing random modifications in this file, right? This sometimes doesn't work well, but an extra step that some hackers do, they create like a grammar that specifies what is valid, right? They create random modifications that satisfy some properties that should be satisfied by the input format, right? It's really sophisticated stuff. I never imagined that someone would be willing to do that just to hack a system, right? It's a really sophisticated piece of code. In the same way people use fuzz testing to hack systems, in Microsoft, people use fuzz testing to protect the system, to find the bugs before the hackers, right? And this is a very simple technique, but it's very effective. And the idea of using SMT is to try to automate that. Instead of doing random modifications, right, you do a next step, right? You try to find some inputs that's going to exercise some specific path in the program. I have here a very simple program that computes the GCD of x and y. And just to give an idea on how this stuff works, let's assume that we want to execute the loop twice, right? You want to find the input for x and y that's going to execute this loop twice. The first thing, I'm going to unfold the loop, right? I create a copy of the loop. Now I have a sequence of operations. Doesn't make sense in logic, you cannot say x equals x plus, well, you can, x equals x plus 1, but this is false, right? In this way, you cannot simply convert your program to a formula. There are several ways to avoid this problem, but one is to use static single assignment form, right? Every variable now is assigned only once now. Basically, I have two sets, actually three, the zeros, the ones, and the two variables, right? Now, since I want to execute this loop twice, I have to, the first condition should be false, right? Otherwise, it's going to be executed only once, but the second should be true, right? In this way, we can map this stuff to the following formula, right? Now we have a formula that you can send to Z3 or any other SMT solver. Let me point out that you have the modulo operator here, and probably you care about precision. In this way, instead of using integers, right, you use bit vectors, right? Because here you want machine arithmetic semantics, right? And you send it to execute some SMT solver, and you get a model. Now, in this model, tells you that setting the inputs to 2 and 4, you're going to execute the loop twice, right? And that's the same idea people do for the exploits, but instead of having a small program, you have a gigantic program, and they're going to convert to a bunch of a big conjunction formula that's a big conjunction sent to SMT solver. These formulas are big, but they are very simple, right? Oh, let's talk another interesting thing. Suppose that we may ask if we remove this requires this precondition saying that y0 is greater than 0. Why did I put that? The problem, in the first time I tried this example, I actually tried in our tool, and without y0 equals 0. What the SMT solver did was to satisfy the formula setting y0 to 0, right? In the SMT solver, in first order logic, all functions are total, right? And how do we model partial functions like modulo, division, and so on, right? How do we do that? A trick that we use is very simple. Suppose that, for instance, division by 0, right? Instead of saying that we have a partial function in our SMT solver, division is still total, but it's underspecified. We don't say what's the behavior of division when the second argument is 0. It's like an uninterpreted function, right? In this way, every partial function can be converted to a total one using auxiliary uninterpreted functions. The behavior, like is saying, I don't know what's, division by 0 can be anything, right? And since if you have y0 greater than 0, if you don't have this precondition, it's really easy to satisfy, right? Because you can, x0 modulo y0 can be anything. This way it's really easy to solve the problem, right? But you may say, oh, but now I need to put these preconditions. No, you don't. But the tool is going to tell you, it's going to point to, oh, there is a test case where you're setting the argument to 0, right? It's like pointing to you that there is a bug in your program, right? You can exploit some unspecified behavior. Okay, the whole loop, how they use actually implemented this stuff. The idea they start running the program with random inputs, right? They start with a valid, for instance, they found a bug once, they got a valid video, MPEG video, start running, doing some random modifications in the video, trying to execute, to do path coverage, right? But eventually there are some paths that they cannot execute. They cannot find inputs to exercise a particular path. At that point, they use this technique I described, right? They convert this path they are failing to execute, they convert it to a formula and call SMT solver, right? And this technique was introduced in 2005. It's called Dart, right? That's combining randomization with the symbolic simulation. And there are several Dart-like projects in Microsoft. We have Sage. Sage basically is Dart for x86, right? The idea here is that you are getting a binary, not a actual program, and you can do the same thing. The same idea works. You can get every machine instruction, and you can create a formula associated with this instruction. We have PEX, that's for .NET, right? I'm going to talk a little bit about PEX later. And PEX is higher level, right? You have the idea of parameterized unit tests. Instead of writing unit tests that's testing just one test, it's like a parametric one. And you can use this kind of technique to find arguments that increase your code coverage. And we have also Yogi. One that's interesting is this Vigilante. The idea here is that they put a honeyspot on the internet. Basically, it's a web server running on a virtual machine, on a sandbox. When there's some exploits, they can catch the exploits because it's running on a sandbox, you can catch. And after that's what they do, they know that there's some worm or some attacker trying to exploit something. They now try to generalize the exploits using this idea, right? They create a symbolic path for that trigger the exploit, the same execution path, and now they try to find other inputs that are going to trigger the same exploit, and they create like a filter blocking this kind of attack. The experience of Sage found several bugs, really important bugs in several components, right? And some of them are really hard to reproduce. I mean, I think that one important thing about finding these bugs, if you find a bug that's with random testing you can find, nobody cares, right? They don't care about your tool. They only care about bugs that they tried really hard to debug the program that debugging for ages and they never detect the bug. That's the kind, these 25 are bugs like that. Sage found much more, but some of these bugs are similar to the bugs they already had and they don't care. Okay, PEX is for .NET. Basically it's monitoring the execution of a .NET application. And it's basically the same idea for .NET. And it found several bugs in the .NET libraries. And the cool thing that is free now for non-commercial use, you can download is a plugin to Visual Studio. It's really, the packaging is really professional. It looks like a product from, instead of being a research prototype. And maybe in the next version of Visual Studio is going to come with Visual Studio. But you can try now. I mean, you can download, install in your Visual Studio, and you can keep playing with all these tools. The tier prover here is completely invisible. You don't even know that it's running. But you are going to see that you are going to find test cases that are really hard to find by random testing. Okay, how this test case generation, all these projects affect the development of a SMT solver? There are 4 items here. The first one, these formulas are big conjunctions, right? I mean, if you're running a program for a couple of seconds, right, you execute a huge number of execution operations, right? In this way, having a really good preprocessor in your tool is really important. This preprocessor, 2 techniques that are very helpful is to do simplification and eliminate variables, right? Most of the variables can be eliminated doing things like Gaussian elimination. This has a significant performance impact. Your solver should be incremental, right? Because you are solving several similar problems. Sometimes what they're going to do, suppose that you want to find a solution for this path. But after you find a solution for this path, you're going to find a solution for a slightly different path. It's the same set of formulas, but with a slightly different tail, right? In this way, it's really nice to have a solver that's incremental, that has support for reusing work. Another thing is this idea of small models, right? What I mean by small here is that given a set of constraints, they don't want an arbitrary model. They want a model that minimizes the value of some variables, right? This may look bizarre, but there is a good motivation for doing that. Because suppose that when you're generating a test case, there is some variable x there, right? That's the amount of memory you're going to allocate. right? You don't want a test case that's going to allocate 4 gigabytes, right? You want a test case that allocates a really small chunk of memory. You want something that's efficient to execute. In this way, you want to minimize the value of some variables, right? And that's the whole idea. And how do we do that? I mean, if you have an incremental solver, one cheap solution is to do the following thing. You process, you call SMT solver to solve C, you get a model, right? Now you pick any one of these x that is big, right? Suppose that there's a x that the value is really big. And I just add a new constraint. I say, I add this new atom, x less than c, where c is a small constant, right? I'm saying, try to find a new model for this new set of constraints where xi now should be less than c. And you keep doing that. You keep adding more constraints, trying to find models where the value of these variables are smaller and smaller, right? And the only problem with this refinement that is like a greedy solution, right? You can make a bad choice, right? You may pick an x that is bad, right? You try to minimize it, and you may prevent you from minimizing a lot of other stuff. But you can use, in your API, you have ways for allowing the user to do push and pop, to do backtracking, control the backtracking. You can retract these bad choices. Finally, there is a trade-off between precision and performance. You have arithmetic. The procedure that I described yesterday was about arithmetic, right? But sometimes you want to be really precise. You want machine arithmetic, right? You want to be able to model overflows. You want to be able, and another advantage of machine arithmetic is that you can handle the nonlinear operators, right? You can handle division, multiplication, modulo, everything. But it's much more expensive than linear arithmetic procedure that I described yesterday. For instance, in Sage and PAX2, the user can use flags to control the precision, right? If you want to use machine, arithmetic, or arithmetic. Okay, the verifying compiler. We say that a verifying compiler is one that can check the correctness of the program, right? But we say, what does it mean a program to be correct, right? Well, correct here, the meaning, I think Tony Hoare gave a really good definition. The idea is that you put a bunch of random redundant annotations there, right? You're going to check, basically you're writing the same thing 2 different ways. You have these redundant annotations, and you have your program. You're going to see if they match or not, right? Of course, everybody that uses assertions, they're going to find out that in some cases, your tool say, oh, this assertion was violated. It's not your program that's wrong, it's the assertion that is wrong, right? This happens all the time. I mean, you write assertions that are wrong, right? And the same, in this way, even if you prove that all assertions, none of the assertions are violated, right? Doesn't mean your program is correct, right? You may have completely different view, wrong view what the program is supposed to do, right? In this way, program correctness is like that. You write twice, you have redundant stuff, and you check if the redundant stuff is compatible with your program, right? Well, spec sharp I'm not going to talk about. We'll some talk on Monday and Tuesday about spec sharp. I'm going to talk about the VCC and Havoc. The motivation for VCC was the verification of this Microsoft hypervisor. It's a meta operating system. It's a thin layer that allows you to run different operating systems in your machine. And a critical property that you want to verify is that it really simulates a number of virtual x64 machines, right? It's like, if I'm not wrong, it's 60 or 70,000 lines of code. It's really a grand challenge to verify this piece of code. And for doing that, people built, they're still building VCC, right? It's like spec sharp, but for C. Right? It has the memory model is really low level to allow you to be precise at the bit level. And basically, it's 1 year old now, but there is a multi-man, multi-year effort here. Havoc is another verifier for C, but the main difference to VCC is VCC wants to reason at the bit level. Here you want to be able to reason about data structures. You want to be able to reason about double linked lists, about trees, single linked lists, right? And actually, Havoc was used to verify NTFS, and it found 50 bugs. And the cool thing here is that these bugs were, I mean, NTFS is there for ages, right? And it's a really solid piece of code. And half of these 50 bugs were confirmed by the product teams, and were really dark corners. I mean, how they did that, right? They had to specify what was simple properties they were verifying, like locking properties, and they wrote these specifications, 250 lines of specification. After that, they had to annotate the code, but the code is huge. And basically, they introduced 600 lines of manual annotations, right? Basically, putting pre and post conditions, right? But one thing that Ruslan didn't mention during his talks, that way to giving some annotations to infer others. Ruslan has a paper called the Houdini method, and this method was used here to infer 3,000 lines of annotations automatically, right? And what's important for all these projects? I mean, the main problem in this kind of tool that they make a heavy use of quantifiers, right? Basically, where these quantifiers are coming from, basically, they use them to model the runtime. Ruslan mentioned that they use frame axioms. You use them to encode frame axioms. If you remember in his lecture yesterday, he had this heap. The value of the heap is equal to the old value of the heap if something is satisfied. And sometimes the user also wants to also have post conditions that contain quantifiers. For instance, if you are writing a sorting algorithm, you want to say that array is sorted, and you need a quantifier for saying that. And finally, some users, I mean, they need decision procedures that are not available inside of your theorem prover. Right? For instance, they need partial orders, right? Since this stuff is not built in, the idea is to axiomatize this theory using quantifiers, right? And view this as a prototype of a decision procedure. As I said in the beginning, the point here is to be fast on satisfiable instances, because everybody only cares about bugs, but you want to minimize the number of false positives. And there's this trade-off between precision and performance that's really important here. And the main point this is a really tough goal because first-order logic is undecidable, and it's even worse in our case because you have arithmetic. It's not even undecidable; it's incomplete. This combination, right? And the technologies that we have in Z3, basically, as I said before, we have heuristic quantifier instantiation, decidable fragments in superposition calculus engine. Another application is SLAM, is a device driver verifier, is a software model checker. The main target here is to model check device drivers. Again, they're checking for simple properties, right? And the architecture of this tool, they have basically 3 steps. You have an abstraction tool that converts a C program in a Boolean program. A Boolean program is like a C program, but all variables are Boolean, right? So you don't, everything was abstracted away. You don't have integers. I'm going to show how this is done. After that, you have a model checker for Boolean programs that has nothing to do with SMT. And finally, you have a model refinement tool. Because since you have abstraction, if the model checker finds a bug, maybe it's not a real bug, right? If it doesn't find a bug, it means there is no bug. But if it finds a bug, you have to check if this is a real bug. And you have this model refinement tool, right? You're going to check if the counterexample is a real counterexample. If it's not, you refine your abstraction and you keep iterating this loop, right? And basically, SMT is used in the first and last steps. Let's see how do we do abstraction. Suppose that you have a program P. I'm going to select some predicates. I mean, basically, these predicates are telling things that I want to track, right? Here I have a small example. I want to track if the variable x is greater than 0 in every point of the program. Or I want to track if x equals y, right? That's the information I want to track that I think are important, right? And now I'm going to produce a Boolean program. This Boolean program is going to have the same control flow structure, But we are going to replace all variables by Boolean variables b1 to bn. Each one of these Boolean variables represents one of these predicates, right? And the idea is that if I prove that a property is true for this Boolean program, it's also true for P. For doing this abstraction, there are two functions that are implemented in SLAM, SDV. We have the implies f. It's the best Boolean function over f that implies E. Basically, try to build a Boolean f using the predicates you have, and try to build the best function, Boolean function you have that implies E, right? And you have the implied by, that's the dual, right? You can implement the implied by using the implies. But the whole point is that the implies you can implement it the following way. First, defining a little bit of terminology, we have this idea of a mean term. It's a conjunction of literals, where we covered before, a literal is an atom or the negation of an atom. And the implies f basically can be described as this disjunction of all mean terms that imply E, right? A very naive approach is to enumerate all mean terms, right? The problem is there are a huge number of mean terms, 2 to the n, right? There are several optimizations, but let's see how can we do the abstraction, a small example using the naive approach. Suppose that I have this expression in my program, y greater than 1. And my set f of predicates contain only two predicates, x less than y and x equals 2. I'm going to enumerate all combinations. We have 4 because we have only 2 predicates. And only the last one implies y greater than 1. In this way, that's our abstraction, right? X less than y, x equals 2. I mean, keep in mind, the actual Boolean program, we are going to have a variable b1 and b2 in this way. We are going to replace y greater than 1 by b1 and b2, right? That's the whole point of the abstraction. Okay, finally we have Newton. That's the, when you find a counterexample, Newton is going to kick in, and basically what it's going to do is like the test case generation, right? The Boolean program is telling you which path should be executed. Now you can do like the test case generation. Is this path feasible? Right? If it is feasible, great, we found a real bug. If it's not, let's try to look into this path and try to find new predicates, and try to abstract the program using these new predicates. And again, we're using SMT for doing that. Okay, what's important here, right? The first thing they want in a SMT solver is the possibility of returning several satisfying assignments instead of running only one, right? If you have only Boolean variables, this is easy, right? To return, well, easy. It's very expensive, but it's well defined, right? Return all possible solutions, all possible satisfying assignments. You compute all possible models of this formula, right? For SMT, it's not clear what do you do, right? You have potentially infinite number of models, right? You have x greater than 0, you can have a model where x is 1, a model with x is 2, x is 3, and so on, right? In this way, usually what they ask for an SMT solver is to be able to return all possible Boolean assignments of the atoms, right? We know that each atom in a SMT problem is talking about tiers like x equals y or x greater than 2. You don't care about models, different models assigning different values to variables, but you care about different models giving different assignments to these atoms. And they also care about unsatisfiable cores. Unsatisfiable core, if you have a big formula, you want to know that is unsatisfiable, you want to know a subset of this big formula that's also unsatisfiable. This is very easy, this is very important for doing in the abstraction refinement step, to know which parts of your path were not satisfied. Let's go back to see how you can use unsatisfiable core. Suppose that you have an abstract path, you convert it in a concrete one, and now you say, oh, this path that you think is feasible is not feasible, but it's not feasible because of this condition in this if. In this way, you get this expression that was not satisfied and add it to your set of predicates. And now you do abstraction using this information. That's why they care about these unsatisfiable cores. Other applications, Microsoft termination, I mean, there is a tool called Terminator for checking if a program terminates or not. It's also used for device drivers. It's also using SMT solvers. Security protocols, there are some high-level language for describing security protocols, and they need to discharge verification conditions using SMT solver. Users application modeling is also a modeling language for business applications. Cryptography, I mean, here it's really hard to break ciphers, but sometimes what these guys in cryptography team, what they do is they have really clever algorithms to break some of these ciphers. It's not feasible to send this problem to SMT, the whole problem to SMT, because it's a really hard problem. We don't have any built-in support for breaking ciphers, right? It's going to run forever. But what they do is to break a cipher, they have sometimes to solve really several smaller problems, and they use SMT for doing that. There are a project for verifying garbage collectors, also using SMT. Another cool idea is model-based testing that I didn't cover here, that's using the SQL Server team. The idea, what they do there, the testers are really sophisticated guys. I mean, much better than most developers I know. They really know theory and implementation. Basically, they create a model, a high-level model of the system they want to test in a high-level language. And they use SMT to generate test cases based on this high-level model. They want to check if the program they are testing really conforms with this abstract model they have. Also for doing, SMT is also used for doing semantic type checking for D. And we hope to have more applications coming soon. Now I'm going to talk a little bit about other applications that are not, I mean, there are users in other places, not necessarily Microsoft. One that is bound model checking is, the idea here is that this technique is used to verify embedded systems and reactive systems. I like small controllers that are described in some language like Lust or Astral, right? These systems you can view as you have initial states. You can compile Lust or Astral to a mathematical formula that describes your initial state. You have a transition relation, right? Probably you have some inputs from your environment. And here suppose that you have this int and you want to know if some property P, some invariant P holds, right? In the first case steps. You're not trying to prove. You just want to know that if this property holds in the first case steps. You can create the following formula, right? You create several copies of your state, k plus 1 in this example. And you say, the first copy satisfies the formula that describes initial state. And now I say the transition relation, right? I'm saying that S1 is a successor of S0, S2 is a successor of S1, and so on. In this way, the first part of formula with int is basically saying this is equivalent of saying there is a path with k steps. And now I don't want just a path with k steps. I want a path with k steps such that one of these steps falsifies the invariant. If this formula is satisfiable, you found a bug. If it is unsatisfiable, there is no bug in the first k steps. Okay, this is not full verification, but you can do a trick. You can try to prove this property using a technique called k-induction. K-induction is like induction, but instead of doing only one step, you do k steps. Basically, you suppose that your property is valid. You have a sequence of k minus 1 steps, and you assume that in the first k states of this sequence, the property holds. And now you try to show that in the next state, the property doesn't hold. If this formula is unsatisfiable, it means that there is no way from a sequence of k steps that satisfy the property, you can go to a bad state, right? Since you proved that there's no way from having a bug in the first k steps, now you can use the arguments. Okay, there's no bug in the k steps. Since this formula is unsatisfiable, there's no bug in the k plus 1, there's no bug in k plus 2, k plus 3, there's no bug at all, right? You may say, oh, this solves everything. No, it doesn't, right? The problem is sometimes if P is not strong enough, what's going to happen? This formula is going to be satisfiable with a S0 that's not reachable. It's not a reachable state, right? You're not saying anything about S0 can be a arbitrary state in your system, right? In this way, like in induction, you have to do things like to strengthen the invariance. Like when you're doing proofs by induction, usually sometimes you have to prove something stronger, right? And the same thing happens here. You have to create a stronger P, right? But again, I mean, there are several heuristics to strength P, but again, this step needs human interaction, right? But that's one technique people use, and completely based on SMT or SAT, right? If you can encode your problem using a SAT solver, you can use the same. You can apply the same technique. Scheduling, right? This, I think, is a good exercise to try to encode scheduling problems using SMT. Right? You have J jobs, M machines. Each machine is a sequence of tasks, and a task is a pair machine. You have J jobs, M machines. Each job is a sequence of tasks, and each task is a pair machine and duration. Basically, here we have an example. We have 4 jobs. Basically, I'm saying job A should execute on machine 1, should take 2 time units, and after that should execute on machine 2 and take 6 time units. I want to find a scheduling that minimizes the amount of time to execute all jobs, right? This is hard. You can make it as hard as you want. And what's the trick here? You can encode saying in SMT, SMT is not optimization, right? But you can say, is there a job? The first thing, figure out that there's the trivial scheduling, right? I can add the times, right? Do a sequential execution, right? You know, I know the worst case, right? And I say, okay, I know the worst case. Let's say it's 30 time units. I can create a SMT problem saying, can I solve this problem in 15 time units? If it's satisfiable, let me try with 10 time units. If it's satisfiable, let me try with 5 time units, and so on. You keep playing with this value. Again, you're solving several similar problems, right? If your solve is incremental, is a big plus. But I think it's a really nice exercise to try to encode this problem using SMT. Planning is the same, is a similar idea. Here I have a simple problem, right? Actually, if you go to the SMT lib, this problem is there. I mean, you have a T trucks, and each truck's located in a city. You want to move packages between these cities, and each step you can build like a transition system, saying, oh, in a step I can move a truck to a different city. I can load and unload a package, and I want to minimize the number of steps. Right? It's the same idea. It's pretty similar to job scheduling, and you can find in the SMT library this problem is there. This planning problem, but again, it's a really interesting exercise. Max set, right? Max set, you can do max setting at max SMT, right? One trick that we can use, suppose that you have a big formula that's unsatisfiable, but you want to find the maximal subset that is satisfiable, right? How can we do that? One way, for every constraint AI, big AI, I create a new fresh Boolean variable, and I transform this guy in a disjunction, right? And now I want to know, I want to minimize the number of Ks. A K, that's the number of AIs that's assigned to true. The whole point here is that assigning AI to true is like deleting the big AI, right? If you assign AI to true, this disjunction is satisfied, right? It's like removing the big A, right? Everybody sees that if you assign the little a to true, it's like deleting the big A, right? If you assign the little a to false, it's like keeping the big A. And so the trick here is to try to minimize the number of little a's that's assigned to true. Now you can create a formula that says I have at most k little a's, right? And you can use the same trick. Keep reducing the k until you find the minimal, right? And the weighted max set can be encoded in a similar way. Suppose now that each constraint has a weight, right? And now you want to minimize this formula here, right? You have this sum, right? And you want to minimize it, but you can use the same technique. Several satisfying assignments. When I was describing SLAM, I said that all set they want all set, and Spec Sharp, for instance, wants several satisfying assignments. What they want is they want to find different bugs, not just one. They want to find several bugs in the program. Right? They have a formula. They want to find different ways to satisfy the formula. How can we do that with SMT? Well, one trick that we can do is that suppose that we have a formula F. The set solver tells us the formula is satisfiable and returns us a model. Right? What can we do is we create now. We have the model. We can create a clause that says this is not a model. So suppose that in this model x is 1. Right? I can say I want a model where x is different from 1. I add this new constraint and try again, execute the solver again. That's the basic idea. You can have different criteria for blocking the current solution, right? For instance, one criteria that Russell uses is that sometimes he doesn't want a bug to the same control point in the program. Even if the set solver can find a different path to the same bug, he doesn't care. What he really wants is bugs to different control points. That's the kind of blocking clause that he creates. He says, oh, I don't want bugs that go to this control point. Since you don't want bugs to this control point, if the SMT solver finds a new bug, it's going to be to a different control location. Let's finish. I mean, the main idea is that SMT solvers are now mature and powerful tools. This is a hot area. People are making improvements every year. SMT is hot in Microsoft, or at least we like to believe it is. We have several applications. NZ3 is our SMT solver. Before I finish, I'm going to point out just to some reading material. We have these 2 books, right? I think we don't have a lot of books in this area, but there are these 2 books. Now you can use them for reference. Some web links. I mean, I'm going to put my slides there. In Z3, you can find all papers about C3. SMT-lib is a really good source of information. You can find a lot of benchmarks there. Lab exercises. I mean, in our website, we have some. Let's see if I find it. If you are teaching a course about SMT, we have really good exercises that people can do solve practical problems using SMT solver. The idea here is that we have a sequence of problems, right? Basically, maybe for a course it's too much to ask someone to build a SMT solver, but you can ask them to extend one. You can use the API of existing SMT solver to solve problems. Like this, the first exercise is to encode the any queens problem using SMT solver. And some of the students are going to learn some of the ideas without having to build everything from scratch. For instance, I'm going to show one that's exercise that's interesting. For instance, this one here is quite interesting. We have in Z3 the theory of arrays, but you don't have the theory of queues. This exercise is asking the student to implement the theory of queues using the theory of arrays. And this can be done using the API of the SMT solver. And I think it's a quite interesting exercise to have in a course about SMT. There's another one about recursive data types, how to encode them, have a soft encoding of recursive data types. It's just, you can find this lab material in our website. Okay, in the end I put several references. I'm not going to go over them, but you can check them. I'm going to put the slides online, and you can see, check these references for information about the topics we covered during this lecture. Well, this concludes my talk, and thank you very much for the attention. I hope I didn't make you suffer too much. Okay, thank you.